Right. So this ties together some, I think, loose ends. The first question, is kind of fun. Like on homework 4, we had this question that if you have a finite ring, then every element's either a unit or a zero divisor. This actually can be generalized to, and I think you did for Artinian rings on your homework, something like this. Actually, it can be generalized further than this. Show that if R is a zero-dimensional ring, then any non-unit of R is a zero divisor, right? So this goes all the way up to zero dimensional. Number 2, in this problem, what we're going to do is we're going to finish off this connection for what I call the fourth property of Dedekind domains. That is, every non-zero proper ideal is a product of prime ideals. We showed that if you're Dedekind, then it follows that every non-zero prime ideal or every non-zero proper ideal is a product of primes. We actually showed that in class. The idea of this is to do it in reverse. That is, show that if you have a domain that has a property that every non-zero proper ideal is a product of primes, then in fact it's Dedekind. So part A is to kind of help you down the path. And it's interesting in its own right too, and it gives you uniqueness. So suppose Pi and Qj are prime ideals of R, and assume additionally that each of the P's, assume that they're another typo, spelled correctly, but invertible. That's what we need. I'll fix that as well. Show that if each Pi is invertible, if you have a product of the Pi is equal to a product of these other primes Qj, then n equals m, and there's a sigma and Sn such that, so in other words, you get uniqueness of length and factorization, right? And as a nice little corollary, it turns out that all the Q's have to be invertible as well, right? Number B, show that if R has the property that every non-zero proper ideal is the product of prime ideals, then every prime ideal is maximal and invertible. Conclude that R is Dedekind. Again, the wording is supposed to help you. Really all you need is that every non-zero proper all you need to do is show that if every non-zero proper ideal is a product of prime ideals, then every prime ideal is invertible, and that'll do it for you, right? Why did I put maximal in there? Because I think it will help. It will help if you show this first, and then use that to show that every non-zero prime ideal in this situation is maximal and then invertible, and then conclude instead. And finally, number 3, this is another loose end that I wanted to tie up. We were talking about all this business where we built proof for domains from the integral closure of a ring and some extension of the quotient field. Suppose you have an integral domain R with a quotient field K, let F be an algebraic extension, finite or not. If T is the integral closure of R and F, then show that the quotient field of T is precisely F. Show that when you take that integral closure, you've got this new ring, show that its quotient field is there. One direction is easy, and the other direction is not too difficult either. Any questions? All right, well, have fun with that, I hope. And
you said directions, but there is only one direction.
what's the last?
If I don't know.
No, containment. Containment is what I meant to say. Yeah, so, right, you're trying to show that, the quotient field of T is precisely F. There's 2 containments to be shown. I shouldn't have said direction, I should have said containment. One of the containments is equal to the other one's, oh, it's still not hard. Okay, any questions? All right, so let's hit this up. So I know Bradley is just dying for this because really one of the big things that we have is we have this big theorem that says if you have a overring of a one-dimensional Noetherian domain that is not the entire quotient field, then it is also a one-dimensional material. So we're going to set about showing this. Now, what we're gonna need is a little background first. And the first thing I'm going to do here is, I'm gonna give you this here. Well, I'm gonna call it proposition here. No, actually, I'm gonna start even further back, limit. So this is unnumbered, I'm going to this way, so help the notes here. Suppose you have an ideal computer room, then this will be useful. This isn't hard to prove, well, I'll go through this quickly. But radical, so notice in general, notice that, in general, you have this containment, right? I don't expect equality. For example, if I equals J, I usually don't expect equality from that. I would have to be an idempotent ideal. Can anybody name a situation where you get, where you actually do get, equality here?
Maybe.
What's in it?
Primes of PID.
Okay, right. Let me say something more general. How about comaximal? If I and J, so if I plus J is the whole ring, you get equality here. So in particular, so we've got that, right? So far, so good. Let's do this containment here. Well, so if X is in the radical divisor, say J, then a big enough power of it is in I intersect J. So X is, a power of X is in I, a power of X is in J, so X is in the radical I and in the radical J, right? So I've got all the inclusions going from left to right. Right, okay then. So to finish this off, this off this way. Suppose X and then radical I intersect radical J. Then X at the end is in radical I, or I'm sorry, in I, X at the end, J. So X to the max right?
Why not x to the n plus m, and we already have the containment of the first one, that's it, right?
Well, right, so we have here, so X.
Okay.
Right, therefore. Okay, so this is kind of neat because sort of doing radical sort of tears apart it puts back together products and intersections, right? Which is kind of, can be useful. So let me give you this proposition here. And I'm gonna say this a little bit more generally than I'm gonna need it in SQL. Suppose I satisfies the ascending chain condition on radical ideals. Then every radical ideal, no, not I. My bad. Suppose R satisfies the ascending chain condition on radical ideals. What do I mean by this? This is a generalization of Noetherian, right? Noetherian means you satisfy the ascending chain conditions on all ideals. This one means it satisfies the ascending chain condition on radical ideals. Can anybody, by the way, before I run off into radical land, can anybody give me an example of a ring that is not Noetherian, but it satisfies the ascending chain condition on radical ideals?
Valuation domain on dimension two.
What did she agree is? That's exactly right. If you have a valuation domain of dimension 2 or higher, that's right, it can be Noetherian, and it has, it's only got 2 prime ideals, so it's only got 2 radical ideals, right? So that's a kind of an easy example. Any finite dimensional valuation domain besides, and there's a, and of course, once you get an example that easy, that means that they're all over the place in nature. So, then every radical ideal of R is the intersection of finitely many primes. And that is to say, another way to think about this is, every ideal is contained in only finitely many prime ideals that are minimal over it. It might be contained in infinitely many. Let me give you a good example. If you look, so let me give you a quick example of what I mean. Let R be well, I just depends on what the field is. So how about this? X cubed minus X, right? Well, this thing is actually UFD, so I can list the minimal primes that contain this. Oh, they are. Well, those 3 will be the prime, and you didn't factor your X squared minus 1. That's what's going on there. But, and that's why I changed it from minus to plus, because if that had been a plus, the X squared plus 1 may be prime, may not. It depends on what's going on in the field. Right. However, but if I call this F, et cetera, et cetera. So the element X, for example, I don't know what I'm doing here. Oh, no, F. The element F is contained in every single one of these maximal ideals, which are all prime, but there's only finitely many that are minimal over it. And that's kind of the difference here. So every radical ideal is, a radical ideal is of course the intersection of all the prime ideals that contain it. So a radical ideal, and in general, any ideal is contained in only finitely many prime ideals contained. Okay, why is this true? So I'm gonna sketch a proof of this proposition here. Let's see here. Suppose there is let me say a radical ideal. That cannot be expressed as an intersection of finitely many times. Okay, so suppose that there is such an animal, right? What next? I claim that there must be a radical ideal that is maximal with respect to this property. Of course, how come? What's that? You don't need
We
Zorn.
got ACC.
Oh.
That's right. So, right, I mean, I've actually already applied some voltage to this, right? I mean, we've got the ACC on the radical ideals. That means that there exists, we can assume I is maximum with respect to this property. Now, this is sort of like Zorn without having to use the steroids, right? So, so there's an ideal that's maximal with respect to this property. I'll give you a hint. I'm going for a contradiction here.
It can't be prime and we're gonna prove it's prime.
That's essentially it. That's what's going to happen here. So, right. I'm going to show, this can't be prime, but we're going to show that it's prime. So, if I is not prime, prime A, B, and R with A, B, and I. Okay. Now consider A and B are not in I. Notice that Why is this? Because this is properly bigger. These ideals are properly bigger than I, so the radical is probably larger. So by the maximality of I, you can realize both of these as a finite intersection primes. Right? So let me write down this collection of um, actually, I guess I'm gonna do it the other way. I'm gonna start from the other end here. This is contained in correct? Because certainly the radical of I is contained in this, and the radical I is contained in that. Right? And this is equal to which is well, actually, which right. Containment, right? Yeah, that was contained, yeah. Contained in I. Because all this crap's contained in I, because AV is contained in I. Right? Which is I. So my conclusion is that I is equal to radical IA intersect radical IB, which equals Q1 UN, Q1 UM, and there's prime, not prime. So there can be no ideal at all that, radical ideal section of a finite number of problems. Let me give you any questions on that?
So Arn's lemma wouldn't have been enough to get this maximal I, because otherwise this would be true for any ring with one, right? That we really needed ACC.
Yeah, I see, yeah, that's right. Because there are certainly, there are certainly,
We need to find the maximum chain.
well, I think the point is, the point is that you're not gonna be able to get this result right here without the ACC. Right, I think that's the point he's making. Let me give you a corollary. If R is Artinian, and of course, this is ACC on all ideals, but I bring this up because of course, Artinian is one of the most important classes of rings. every ideal is contained in, only finitely many primes. Many primes. So, let me make clear what I mean by this. What do I mean by minimal prime? I use this terminology. Well, if I walk up to you on the street and I'll just make that proper. If that's a prop, it's certainly true if it's a ring because it's contained in no minimal primes. If I give you a proper ideal, it's contained in a maximal ideal, right? So because of that, every proper ideal is contained in a prime ideal somewhere. And the minimal over I if the prime and if we have the Q prime, then Q. So that's what I mean by minimal. Notice that if I itself is prime, then it's contained in only one prime minimal over itself, namely itself, right? Okay. This will prove useful in the sequel. Here's something that we're going to use that you might have seen maybe in 8510, perhaps. So we're going to take this as kind of a given. Let me remind you, so you may not have seen this for modules, I'm not sure, but you've almost certainly seen this for groups, and the principle is the same. Let M be an R module. A composition series which has always really bothered me, especially given the conversations we were having before class, because they should really call this a composition sequence. Is a chain. And we see how I index this. M0. It's a descending series of R modules, and actually I'm gonna make these all brick, because otherwise I'm kind of being silly. Such that MA mod MK plus 1 is, anybody know what this is? The answer is simple. And that's what the answer is. So that means that this module has no interesting submodules. The only submodule of MK mod MK plus 1 is itself and zero, right, itself and 0. So you probably saw this in the context of groups or abelian groups, where you basically, you squeeze these composition series out and decompose this way into its sort of simplest form. And the fact we're going to use If M has a composition series, then one can refine any series to a composition series, and any two refined series have the same length. Right. Let me reword that. And so we're gonna use the following fact. M has a composition series. Fact I'm gonna use. Then any series. And what I mean by that is a descending chain of submodules like this, where the quotients aren't necessarily simple, can be refined to a composition series. And any two composition series have the same one. So let me do a quick example, to sort of show what's going on here. So here I'm just gonna do a billion groups. This is E modules, right? So here's some composition series. Or here's some series. There's one right there. Oh, Jim, lazy, right? Because this is a series, but not a composition series, because Z mod 48 is not simple. So what can I do? I can refine this. Neither of the quotients are simple. Further, quotient Z2, 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 or I'm sorry, Z3, Z2. Fine. But that's not the only way to do this.
So, just to clarify, the last part, when you have Z2 is contained in Z6, you're considering there the elements of Z2 to be like 0 and 3.
Yeah, like that, exactly. Notice that this is a different composition series for this, because my terms are different, right? At least some of them are. However, the links are the same, right? So that's the content of this. Use that in a moment. Okay, any questions? Okay, so,
What would,
yes,
so you said, if M has a composition series, what would be a scenario in which it would not, when it's like it doesn't satisfy a finiteness condition, so it would be infinitely long?
or Z, for example, won't have a composition series, right? Because, yeah, it's just different quotients, right? Theorem 526. And it looks like I've freaked out and gotten all off case, but we're gonna need, this is some zero dimensional yang that we're doing here. And we're gonna need this to deal with the one dimensional Noetherian stuff that we've got coming up. So, let R the music ring with one. What about this one? Number one, R is zero dimensional. And no theory. Oh, by the way, let me ask you guys something. We talked about Noetherian rings. Can somebody tell me what an Artinian ring is? Right, satisfies the descending chain.
A non-category.
Don't make me cough. Which condition is stronger? Ascending chain,
On,
descending chain,
on the
same,
rings,
independent? What?
on the rings. Which one is stronger? Artinian is pretty underdog.
Yeah, I mean, you would think just, at the beginning of it, you would think, how can they be different, right? Ascending chain, descending chain, who cares what direction you're going, right? Well, you do have a zero. We will answer this question in this theorem here. Any finitely generated R module has finite length.
So this
And this-
the following are equivalent.
Yes, it is. And when I say, has finite length, what I mean, it's got a composition series of finite length, right? Or, has a composition series. 3, R, is finite length as an R model. So in other words, R itself has a composition series. And Eric's question pointed out that, for example, Z is an example of a ring that this doesn't hold for. And of course, Z is one dimensional. 4, R is Artinian. Artinian means you got the descending chain division on it. This, actually, I remember the first time I heard this theorem, I thought it was kind of astounding. Because not only does it mean that Artinian is a stronger statement, it means it's a mucho stronger statement, right? Because Noetherian rings, they're the Wild West compared to Artinian. Artinian is extremely restricted. Because not only your ideals finitely generated, but all your prime ideals are maximal. So it's small. Artinians are Noetherians that just got squished down, right? For sure.
Any Artinian domain is a thing.
Any Artinian domain is in fact a field. That's right. And actually, right, so on the homework, I've just finished grading your number 2 and I'm a little bit through number 3. I will probably get caught up this weekend, so, and that'll give some of you the chance to get caught up too. Anyway, so one of the things to prove in the homework was if you have a finite ring, then every element is either a unit or a zerotizer, right? And in that, Mr. Bradley actually showed it for Artinian, right? He said, oh, look, I can do it for Artinian. And that's true, right? So he got something. And this is even more general. The new homework says you don't even need this, right? You don't, you only need zero dimensional to get that. By the way, my hint on that problem is think of that one locally. Think locally and act globally. Sounds like a bumper sticker, doesn't it? Okay, so note, let me note before we start. I'll probably note it again. Where did my eraser? Am I having a stroke? Oh. It's yellow on my paper. Notice that, the statement that I unfortunately, raised, 3 and 4 are equivalent. And it's easy to see that 3 implies 4, because if you have finite length, then you have to have a descending chain condition. But if you're Artinian, if you have the descending chain condition, then what that gives you is a composition series, and those always have the same length. The remark that we had over. So I am going to spend my time hooking up the other 3. So let's start with 1 implies 2. So we want to show that any finitely generated R module has finite length. So since R is 0 dimensional, all primes of R are minimal and maximal. Right? That they're like an island, right? Nothing contains them. No, well, actually, only the ring contains it. And inside it are ideals usually, but none of them are prime. So the first thing to notice is that R is Noetherian. So 0 is contained in only finitely many times. And I really do mean finite in this case, because here's the deal. We know that Noetherian in particular, it satisfies the ascending chain condition on the radical ideals. That means that there can only 0 is contained in only finitely many prime ideals, because this is true for any ideal. Now, one thing might be 0 itself might be prime, but in that case, what do we have? Right.
It doesn't.
And certainly this statement follows if R is a field, right? Because any finitely generated R module is vector space, and so there you go. So let's focus on when this is more interesting, that is to say when 0 is not a prime ideal. 0 is contained in only finitely many primes, but it's contained in every single ideal. So R has only, let's say M1, M2, Mn as its only. Right, it is, well, it's semi-quasi.
No, it's
Well,
not.
no, you're right, it's because we are assuming a theory here, right? So, consider M1, M2, and product of all these ideals. This is contained in the intersection so the nil. This is the nil radical of R, right? But
So
as M1 up to Mn is finitely generated, again with the Noetherianness, there is a finite power of that ideal that is 0. This is because it's finitely generated, and this is a big application. Anybody want to see me prove that? you do need that you do need that this ideal to be finitely generated, but if you have an ideal, so you look skeptical, so I'll deal with that.
Well, so I was thinking. So you have one containment, for when you say M1 up to Mn is the no radical, you have the one containment for this, from this intersection. And the other containment just becomes because the no radical is contained in every maximal ideal.
Oh, yeah, I don't need this. That's good. Yeah, I'm sorry about that.
Well, won't the intersection.
Well, the intersection actually,
No radical
you
because
actually do
where-
get equality here. Why do you get equality?
Well, the root of this ideal is should be the.
Well,
intersection of-
these ideals are maximal, so they're co-maximal. So the intersection and the product are the same. Yeah.
Well, isn't the nil radical the square root of the zero ideal, which is gonna be the intersection of the primes?
Right, but the question is why is the intersection actually equal to the product? Right, because a priori the product might be smaller than the intersection. But they're equal here because the ideals in the intersection are all maximal. So in particular, they're co-maximal. So, yeah, that works. But it doesn't matter, even if it was a containment, we still get this fact, that this is zero. Alright. So, so in between n and 0, we can insert, let's see,
What's
intermediate modules, NK intermediate modules. As follows, n BMI right? So here's what I mean by this. I can create a chain of modules by going in M1, in M1, M2, in M1 squared, if appropriate, M2, like this. This is what I mean by this. And of course, how many can I insert in the middle? No more than NK, right? Because I can use in most K powers on each of these. Note that B mod BMI is a finitely generated R mod MI module. That's easy to check, right? This quotient here is an R mod MI module. And what kind of ring is R mod MI? Even better, it's a field, right?
yeah.
So, at most, finitely many intermediate modules between B and BMI. Because the modules in between here correspond to subvector spaces of BMI, B mod BMI as an R mod I module. So I've got NK steps, and in between any two of these, I can insert at most in intermediate modules because it's a vector space, right? So you've only got finitely many. And so N has got finite length. And that's what I wanted to prove there. That's what it implies to.
What is N?
N is finitely generated R module.
Okay.
Any other questions? All right, you all then have a good one, and we will see you